Good morning everyone. Today we are going to see topic binary codes, like how it is getting represented in binary and everything. Now generally binary codes are represented in computer applications. Generally they are used for digital communication purpose. Now classification of binary codes. Binary codes are of three types. You can observe clearly: weighted codes, non-weighted codes, alphanumeric codes. These are the three types which are present in our binary codes. So what exactly the binary codes, weighted codes represent? So weighted codes you are having 8421 codes, 2421 code, 5211 code. Now generally 8421 code, 2421 and 5211 codes. All these are weights of the respective positions. Now how we are going to represent those weights in our particular thing we are going to see now here. Now you can observe this 8421 code. If you observe clearly 8421 code, now this is 2 power 0, this is 2 power 1, this is 2 power 2, this is 2 power 3. Means I am having three positional values, that is 2 power 0, 2 power 1, 2 power 3 and 2 power 4. Those are the positions of that given thing. Now for 0, if I am placing all zeros, then the respective thing is going to be the 0th value. Now if I am placing 2 power 0, for example if I am taking the number, you can clearly observe 2 power 0, 2 power 1, 2 power 2, 2 power 3, that is 8, 4, 2. So under 8, 4, 2, 1, if I am placing all zeros, my value is going to be 0. If I am placing 0, 0, 0, 1, then my value is going to be 1 value. Similarly, I am having value for 2, 3, 4, 5, 6, 7, 8 and 9. So this is what the representation goes with respect to the calculations related to its positions. Let's get on to the next thing. See. Now next thing is 2421 code. Next 2421 code is similar to that of 8421 code. Now the representation in this particular thing will go like this. Now for example 2421 means positions for 0 should be 0, 0, 0, 4 zeros. So I am representing 0. For 1, 0, 0, 1. For 2, it is 0, 0, 1, 0. For 1, 1, double 0, double 1. For 4, 0, 1, double 0. So for 101, you can see positional weights as, see, 2, 2, 1. So my total value is giving me as 5. For 6, double 1, double 0. That is 2 plus 4. Next for 7, double 1, 0, 1. For 8, 1, triple 0, that is triple 1, 0. Next for 9, if I am adding everything 2, 4, 2, 1, maximum value that I can represent under 2421 code is 9. So this is what the thing which is present under 2421. Now coming to my 5211 code, you can see clearly that under 5211 code the representation is similar to that of 2421, that is 0, 0, 0, 0 for 0, 1, this is 2, this is 0, 1, 0 for 3, 0, triple 1 for 4, 1, triple 0 for 5, 6 for 1, 0, 1. So these are the values, various values representations in various code representation, that is 8421, 2421, 5211. Let's get on to the next code representation, that is BCD. BCD means binary coded decimal. Binary coded decimal, and in BCD we are going to represent only single digits. For example, if I am having 24, if I am having 24, then I am going to represent 2 separately and 4 separately. Means I am going to represent 0, 0, 1, 0 and 0, 1, double 0. Now this complete value is going to represent as binary coded decimal, and normally in a binary number we used to represent 12 as 11100, but in BCD I am going to represent each digit with 4 bit of information. Means for 12 I am going to represent 00001 and 2 as 0010. So this is the difference between normal binary number and BCD number. Let's see how those values are getting represented here. Now you can see clearly here the representation is for 2, 4, 5. Now I am representing 2 separately, 4 separately and 5 separately. Means I can represent a value in BCD ranging from 0 to 9. I cannot represent 10, 11, 12. When I want to represent 10 and 11, I need to treat each digit separately. Means for 10 I need to represent 0, 0, 1, and for 0 I need to represent 4 zeros. For 11 I need to represent 0, 0, 0, 1 and 0, 0, 0, 0, 1. So this is what independently I need to represent under BCDs. Now coming to non-weighted codes. Let's see, get into the non-weighted codes. Non-weighted codes, we have XS3 number. Now XS3 number means XS3 represents we are going to add 8421 code plus 3 I am going to do. Means whatever the number, if I am having 0, 0, 0, 0, to represent XS3 code for 0, I need to add 0, 0, 1, 1. So my value is going to be 0, 0, 1, 1, 1. To represent 7, to represent 7 means 0, 1, 1, 1 in XS3, I need to add 3 to that 7. So 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 0 plus 1 is 1 with carry 1. Next 1 plus 1 is 0, 0 plus 0 is 0 with carry 1 again 1. So you can see clearly the number for 7 is 1010. So this is how we are going to get here. Generally additions in a binary will take place like this. For example, if I am having a b, if I am added together, so I am going to get some value as well as carry value. So if I am having 0, 0, 0, 1, 1, 0, 1, 1 as input values, some value will be 0, carry will is going to be 0. For 0, 1 combination, sum is 1, carry is 0. For 1, 0, sum is 1, carry is 0. For 1, 1, sum will be 0, carry will be 1. So this is how addition goes. Now when I am doing subtraction, for example a b, the difference will be there and borrow will be there. So if I am having 0, 0, 0, 1, 1, 0, 1, 1 combination, so difference will be 0, borrow will be 0 for 0, 0. For 0, 1 means I am removing a lower number, I am removing a higher number from lower number, means I need to borrow. So borrow will be 1, difference will be 1. So for 1 minus 0, difference will be 1, borrow will be 0. For 1 minus 1, 0 and 0. So this is subtraction and this is addition. So this is how the process flows here. Let's get on to the next thing. You can see here clearly there is an example which is given represented here. The example is related to convert 15 to an XS3 code. So for 15 I can do like this. So I can add 3 here, I can add 5 here. So 1 plus 3 is 4, 5 plus 3 is 8. So represent 4 and 8 in BCD form. So 4 can be represented as 0, 1, 0, and 1, 0, 0. So this is how the representation goes for converting a given binary number to its equivalent XS3 number. Let's see the next example. So these are few of the examples to representing the given BCD number in binary. So why we are using XS3 means code has no limitation. It can be considered simplifying the arithmetic operations. So those are the simple things which are present over here. The next most important code is gray code. Gray code generally we use on Karnaugh maps to reduce Boolean algebraic expressions. So gray code, how to write gray code will tell you. I will tell you a method. First method is mirror technique. How to represent a gray code using mirror technique. You can clearly see. Now these are regular BCD numbers. These are regular BCD numbers. For those base numbers, how I am going to represent gray code? Now see, I am using a mirror technique. For example, if I am taking, I am writing 0. I'm writing 0 and 1. So only these two bits are there. Now place a mirror here. Now place a mirror here. If I am placing a mirror, the number will be looking as an opposite number. Means 1 0. Means 1 0 will be there. Place two zeros on the top. Place two ones in the bottom. Next again place a mirror here. Place again mirror. Now 0 1 double 0 double 1 0. See now here 0 double 1 0. So this is how. Now place 4 zeros. Now double 1 double 0 double 1 double 0. Place 4 zeros on top. Place 4 ones on the bottom. Next again. So this will go repeatedly. So this is how we are going to get a gray code using mirror technique. So this technique we call it as mirror technique. Now apart from mirror technique, we are also having a logic conversion from binary to gray and gray to binary. So this is what we can do using an logic diagram. I will tell you. For example, if I am having binary number to be converted to gray number, generally here we are using an XOR gate. This is an XOR gate. XOR gate function is XOR gate will give me, for example, if I am having A, B and XOR operation means 0 0 0 1 1 0 1 1. So for similar inputs my output is going to be 0. For differential inputs my output is going to be 1. This is the simple operation. For now you can see, if I am having input as b2 b1 b0 and output as g2 g1 g0, now you can see b2 is directly connected to g2, b1 is connected directly to g1, b0 is connected to g0. So using this particular circuit diagram we are going to solve our given thing. For example, if I am having my values as 1 1 0, so 1 will come out as directly 1. This one, now 1 and 1 given as XOR operation. 1 1 means output is 0. Next here 1 and 0, the output is going to be differential input, so 1. So my gray code for 110 will be 101. So this is how we are going to operate for converting a given binary number to gray number. Let's get on to the reverse operation. Like reverse operation means gray to binary conversion. Gray to binary conversion means you can see exactly reverse operation here, but a small difference will be there here. That is, I'm going in previous case G2 B2 was given as G2. Now same thing will go on. But for next bit, what I am going to do, the output is getting connected to the input of next gate. So if I am having gray number as 101, so 1 will be coming as output directly. Next input will be differential input. So output is 1. Next this 1 and this particular 1. So totally these two things are going to represent 1 and 1 same input, so output is going to be 0. So for 101 gray code I am going to get output as 110. So this is what how we are going to represent our binary to sorry gray to binary conversion. So these are the few of the examples how we are connected. See, these are all binary numbers and respective gray code numbers. This is how the representation goes. Some of the few of the conversions are also there, binary to BCD. For example, if I want to convert binary to BCD, convert binary to decimal and decimal to BCD directly. So this is binary. I got my decimal as 29. So 29 can be written as 2 separately and 9 separately. So we are going to get a direct BCD number. So these are the few of the steps which you can follow to represent any kind of number. This is BCD to binary conversion. So these are the few of the conversions which are available for converting one form of code to the other form of the code. You can go through the steps, and there are one and two examples which are available for these kind of, and these are sequential codes and self complementary codes we call them, as these are having a reflection in nature. You can observe clearly that for 241 code we are going to call it as what we call like reflexive code. Like if you can see 000, exactly opposite is 111. Next for 0001 it is exactly opposite to 1110. For 0010 the reflection code is 1101. For 0011 it is 1100. For 0100 it is 1000. So this is what we call it as reflective code, or we can also call it as a self complementary code. So this is what which is present for 2421. So that's the reason we are calling it as self complementary code and sequential codes. So we are going to end our session here. We'll continue in the next